So
Okay.
welcome everybody. My name is Lucy Norval and I'm with the Scarborough Public Library. I coordinate programming and communications for the library. And I want to welcome you all tonight. And I want to welcome Seth Lockman back. So Seth, our NASA Solar System Ambassador, did the night sky tour for us. And it was really awesome. And we've got people who are on this program because they saw you, Seth, during the night sky tour. So Seth manages communications for an aerospace startup, and it recently launched its first rocket. And he can tell you more about that rocket. Seth advocates for the ongoing effort to build a spaceport here in Maine. And as a solar system ambassador with NASA's Jet Propulsion Laboratory, Seth communicates the science and excitement of NASA's space exploration missions and discoveries with people across the state. And part of why he does that, I think it's really important to mention, is that as a kid in Down East Maine, Seth developed an early fascination for the night sky. And we have a lot of patrons who come into our library, lots of kids of all ages who are fascinated by space. And we have a lot of items in our collection that have to do with space. So Seth was guided by his father's love of astronomy, and he quickly learned how to use a telescope and different kinds of star charts. And from there, Seth gravitated toward the amazing stories of space exploration, not just stories of crewed and robotic missions, which we're going to hear about tonight, but also stories of diligent researchers and how their scientific discoveries changed our understanding of the universe. And Seth has a background in science and mathematics. He graduated summa cum laude from the University of Maine with a bachelor's degree in psychology, with a focus on statistics and research. So shortly after graduating college, Seth created a weekly half-hour talk show about the night sky and the universe. And it ran for 4 years. So during that time, after interviewing the CEO of an aerospace startup in Brunswick, Seth left that show to work for the rocket company. And the rest is history. So Seth, welcome back. And thank you for coming tonight to talk about Mars.
My pleasure. Glad to be here. Yeah, Mars is one of those lifelong fascinations of mine. And I actually, when I was in middle school, won a trip to space camp by writing an essay on the comparative geological histories of Earth and Mars. And I will be using some of that information in this presentation.
Cool.
Yeah. Well, hey, everybody. I'm Seth. I'm a solar system ambassador with NASA there. And I am just really happy to be talking with you about the night sky and some of what's in it. So I'd like to start with just a quick little star tour, probably a little quicker than last time. Let's see here. All right. Can everyone see here?
Definitely.
Okay, so this is a simulation of the night sky as you might see near Portland, Maine, if you were to go out in about 2 hours. This is roughly what the night sky is going to look like. So remember this, burn this into your memory, and then just go outside and look up, and it should work. So there's a lot of great stuff in the night sky. Right now, the moon is particularly close to Mars, which we would call it, well, it's not at a conjunction, but it's near conjunction. So getting to see two celestial bodies that close in the night sky, it's kind of like watching airplanes fly in formation. A lot of astronomers really enjoy that. But the other thing that you can do, you can go out and you can face the south. Now, how can you tell that you're facing south? Well, course, you know, maybe maybe there are these nice big red letters on your horizon in real life, but you can use a compass, you can use a phone. Um, although I would advise away from using white light if you can. It takes the human eye about 2 hours to fully adapt to the dark, which is about how long it takes the sun to set. So there might be a connection there. Um, and you really only want to use red light when you're trying to look at the night sky, because red light has the least energetic photons that do the least damage to your eyes. So compass is probably better than a phone, but anything will work. You go out to the south and you look up, and can anybody tell me what they see? Is there any familiar patterns in the night sky here for folks? Lucy, for some reason, I can't see the comments right now. I'm sorry. Can you?
Yep.
Oh.
Yes, people. Orion.
Yes, exactly.
Orion.
Oh, there we go. I know how to use computers. Look at that. This is terrific. Okay. Orion, exactly. Orion. So right here, you can see Orion. So there's the 3 stars of his belt. There's the sword with the little nebula there. And of course, there's Betelgeuse. That's the star that was dipping in brightness in, God, was it last September already? But that was a while back, and it actually it went back almost to its full brightness and then dipped again. And so at this point, we're pretty confident that there's a cloud of gas that the star is emitted. There was a solar flare, a kind of a cosmic passing of gas, if you will, and that gas then blocked the star from our vantage point here on Earth and made it appear much dimmer. Anyway, it got nearly back up to its original brightness or luminosity, and then it dipped again, but not quite as significantly. But that is very, very rare to see a star change in brightness in the night sky. So you can go out and look at it now, and it'll be about 20% brighter, probably 3 or 4 months from now. And that's a very rare opportunity to catch. So I would highly recommend checking that out. The other thing that you can see here is the winter hexagon. So starting from Orion, on his other corner, down on his foot here, we've got Rigel, right? And then you can see that above the ground here, Rigel is, well, maybe not parallel to the ground exactly, but it's about at the same level as Sirius. Now, Sirius is the dog star. This is the head of one of Orion's hunting dogs, and you can kind of see his legs here. He's got a little tail there. Okay, so that's Sirius. So from Rigel to Sirius. From Sirius, you go straight up to Procyon. This is the tail star of, maybe it's Sirius's pup or younger sibling, or who knows, but it's Orion's other hunting dog right there. From Procyon, I go up to these 2 stars. Can anybody guess what those stars would be, or what this constellation would be? Well, I'll tell you. It's Gemini. This one here is Castor. That one there is Pollux. So those are the Gemini twins, the 2 of them. You can kind of see they've got their arms around each other, and they're kind of one arm out like that. They've got their legs down here. Anyway, you go, oh. This moment of cosmic awareness was brought to you by the mundane issue of batteries. Okay. So from Procyon to Pollux, and then right on over to Capella. And Capella is in this kind of pentagon shape here of Auriga, the charioteer. And Capella was thought to be a sun-like star for a long time. We now know that it's a binary system with multiple additional dwarf stars, probably not hospitable to life. But in the original Planet of the Apes, they actually thought before they realized they had traveled through time, they thought they'd landed in Capella in the system. Anyway, from Capella, you go straight down to Aldebaran. This is the eye of Taurus the Bull. Taurus the Bull and Orion, they do not like each other. And so Orion is chasing Taurus the Bull across the night sky. And if you played the sky forward in quickly, or if you were to observe the sky over many hours, you would see Orion kind of go this way, chasing Taurus across the night sky. And from Aldebaran, we go back to Rigel. So that is what they call the winter hexagon. These constellations are all up in the winter here in the northern hemisphere. So again, we've got Rigel, Sirius, Procyon, Pollux, Capella, and then Aldebaran, and back to Rigel. If you have any trouble remembering that, as I do, you well, actually, I don't know if there's a mnemonic device. You could probably make one up. Or you can use one of any number of navigational aids, a sky chart or a planisphere. In fact, the library has a web page where you can go and print out a chart of this month's night sky, right, Lucy?
We have a lot of resources, yes.
Terrific.
And we will share some links to those resources when we share this recording with people. But yes, you can go onto our website and discover all kinds of things.
Excellent. And here, just to show you, Orion really does chase Taurus across the night sky. All right. Let's see if we can pull this down here. And now for our feature presentation. All righty. Now, it's not an astronomy presentation without a laser pointer, so I'm very happy that the Zoom screen share offers me this little red dot. That probably makes me very happy. So, as you may know, the Perseverance lander in Mars 2020 rover landed just yesterday, about 3 in the afternoon our time, and it went flawlessly. And it has yet to deploy this little helicopter over here, which we'll talk about in a little while. But as we speak, Perseverance is about 130 million miles from the nearest road. And it really is quite the all-terrain vehicle. It's meant to run years and perhaps decades without ever getting the oil changed, which is it's a nuclear-powered SUV-sized rover. But the Martian environment is pretty harsh. The dust grains on Mars, especially, they're not really weathered the way the ones on Earth are, and so they wreak havoc on all the rover systems. It has to be a very, very robust kind of vehicle. So before we get into the rover, let's talk about Mars a little bit. Here's a pretty good picture of Mars, and you can see here one of its biggest surface features. So the Valles Marineris here, the Mariner Valley, this canyon is about 2,500 miles long. So this thing could basically stretch from California to New York, all the way across the US, if you were to plop it down here. It runs basically along the Martian equator, a little bit north. It spans about 1/5 of the way around Mars. And it's about 4 miles deep. By comparison, the Grand Canyon, which is not the biggest canyon in the world, but it's probably the most famous, it's about 500 miles long and about 1 mile deep. So this is significantly larger than that. And the way that this this feature formed, this canyon, because the Grand Canyon was formed by a river, and there was probably a river running through the Mariner Valley at one point. But that is a tremendous amount of erosion, 4 miles deep, 2,500 miles long. There was probably something else going on there. And so I'll touch on that briefly in a moment. You also see the Tharsis Mountains over here, the Tharsis Mountains. These are some of the highest mountains, not just on Mars, but in the entire solar system. And just over the horizon is Olympus Mons, the biggest volcano or mountainy thing in the solar system. It's about 374 miles high, and it's got a 4-mile high cliff just running all the way around the bottom. It's so big that if you were living on the side of the mountain, you probably wouldn't even notice the slope. You really wouldn't feel higher up than anything else. Just because it's so big, it's not even possible to really perceive in the way that you might experience a mountain here on Earth. So a couple other fun facts about Mars. And oh my dear, that table did not translate well. I'll do my best. So Earth is about 93 million miles from the sun, and Mars is about 1.5 times farther than that. It's about 142 million miles from the sun. It's smaller than Earth. It's just over 4,000 miles in diameter, whereas the Earth is nearly 8,000. Gravity is about 14% that of Earth. So if you weighed 100 pounds on Earth and then you went to Mars, you'd only weigh 14 pounds. And that's going to be very important later because that's part of how we can land such heavy spacecraft on the surface of the planet, is that the same amount of thrust coming out of a rocket can essentially do more work because the planet isn't pulling on it quite as hard as it would here on Earth. A Martian day is about 40 minutes longer than an Earth day. And this actually does have an effect here on Earth, because if you work with one of the Mars rovers, you have to do everything about 40 minutes later every single day. You have to set your alarm 41 minutes after the day before. And so it can definitely mess with your sleep schedule a little bit. But the rover teams are very dedicated people, just for doing that alone. A Martian year is almost twice as long as an Earth year. So if you lived on Mars, you could drive probably around the time that you turn 7, which is kind of a scary thought, but you'd have aged about the same biologically as people that get their permits here on Earth. The Martian atmosphere is incredibly thin. It is about 0.5% the pressure of Earth here at sea level or near sea level. So what this means is, for example, the dust storm in The Martian that nearly blew the spacecraft over, that could never happen because the atmosphere is so tenuous. If you've ever been in school and they've ever put marshmallows in a little vacuum chamber and you see the marshmallow expand, that vacuum chamber probably had more pressure in it than the Martian atmosphere. So it's very, very tenuous, really not much there. And what is there is about 95% carbon dioxide. Now that's what we humans exhale. That's what we need to get out of our bodies. And so even if you could get some of this atmosphere into human lungs, it really wouldn't work. It's really not good stuff to breathe. And Perseverance actually has an experiment on board that's going to try and help deal with that problem, because we do want to eventually have people living on Mars. The other fun thing is it's got more moons than we do, Mars. We've got one moon, right? Well, actually, we have another kind of pseudo moon, but I think we're about to lose it. So basically, we have the one moon. Well, Mars has 2 moons, Phobos and Deimos. And Phobos is actually on its way in. It's spiraling into the planet, which means that in about 50 million years, either it's going to crash into Mars, or it's going to break up, and then Mars will have a beautiful set of rings, not dissimilar from Saturn. Actually, probably it won't look as good as Saturn. The other really interesting thing, and you may have been seeing some of this with these videos here of flying over, but there are formations that really look like there was water flowing through them, riverbeds and deltas, canyons. There's mounting evidence of, well, we know that there's water on Mars because we know there's water ice in the ice caps, but there's mounting evidence of liquid water on Mars, basically constantly at this point. And hopefully the next mission is going to capture some of those water samples. All right. That's weird. Here we go. Now, you really couldn't tell too well just looking at that red image of Mars. So this is an elevation map, right? These blue areas are very low. These red and brownish areas are very high in elevation. And almost immediately you notice what look at this northern part of the planet, right? And see how low it is. And then this upper part is very, very high up. And that's kind of a remarkable thing about Mars. Earth actually has a similar feature. The Pacific Ocean covers a comparable amount of Earth's surface. It's just this whole, almost half of the planet that's just depressed. We just don't think about it because the ocean is filled with water. And here, of course, on Mars, there's not anymore, at least enough water to take up the surface here. You can also see those 3 volcanoes from that earlier image. And here is the largest volcano in the world that was just over the horizon at the time. That's Olympus Mons. And over here, this is where the InSight lander, a previous mission, detected the first active fault on Mars. So we thought that Mars was basically frozen all the way through. We now know that it still has a molten iron core, and we know that there is some, whether or not there is convection in the mantle, there is some tectonic activity. There are still Mars quakes, and there are still places where the Martian crust breaks apart, and then you can have an earthquake. So it is not geologically dead like we used to think during my childhood. We know that Mars is still geologically active. Although all of the volcanoes on Mars, as far as we know, are extinct. We've never seen a Martian volcano erupt, and we've not seen signs of any Martian volcanoes erupting in the past couple million years. So this has been a really, really good month for Mars. It lined up so that our planets were able to send spaceships. You know, we could send a probe from Earth to Mars for cheap, for very little fuel. And as a result, 3 different countries all decided, hey, we're going to send a probe. So the United Arab Emirates sent the Al-Amal, or HOPE probe. Its mission is to get a full picture of the Martian atmosphere and provide a really big, a holistic view of Mars's climate throughout the year, which again is almost 2 Earth years. This probe had to fire its engine for about 30 minutes, about half an hour of braking, just to slow down from 75,000 miles an hour to about 11,000 miles an hour. These are incomprehensibly fast speeds. You would not, if you were standing still, you would not see this probe go by. This is how fast we're talking about here. It's got a number of instruments on board. Basically, the EMIRS instrument is going to study temperature patterns, ice and water vapor and dust in the lower atmosphere. The imager, the XE camera, is going to capture high resolution images And it's also going to study water distribution on the surface, or sorry, water distribution in the clouds. So it's going to try and study like the thickness of Martian clouds. And then the ultraviolet spectrometer here, EMUS, is going to study the upper atmosphere, looking for traces of hydrogen and oxygen further into space. This is the first image of Mars taken by that exploration imager. So this thing right here. And that is just beautiful. Apologies, I have a bird clock. There are the Tharsis Mountains. There is the Valles Marineris. There is Olympus Mons. And you have enough detail here that you can even kind of see that around this raised area, you can see the beginning of the northern hemisphere and how much lower it is. And you can see clouds forming around a mountain, just like they do here on Earth. So this is a very exciting mission because even though it only has 3 instruments, what we're going to learn about Martian weather is really, really important for settling the planet in the next couple of years, really, not even decades, a couple of years. Now, China also sent a very, very ambitious project. They've got an orbiter and a lander and a rover. They entered orbit 1 day after HOPE, so they did it on the 10th. MOI just stands for Mars Orbit Insertion. And it's a little bit hard to get reliable information on this mission. One place mentioned that they have 13 instruments, but then this promotional material shows a little more than 13 scientific instruments between the orbiter and the rover. The purpose of this mission is largely similar to gather weather data and to also search for water deposits. There's ground penetrating radar on the orbiter and the lander. So the idea is to get these two working in concert so that the orbiter identifies a region of interest, and then once the orbiter has made that detection, then the rover goes over to get a closer look at whatever it is that needs inspecting. We actually have video from the Tianwen probe. And this is right when its engines kicked on to start a 15-minute burn. So it had to decelerate a very similar amount to the HOPE probe, but its engines were a little more powerful and it was able to do it in about half the time. And you can see the Martian surface there, and you can see a couple of craters. All right, we should fade to a camera on the other side of the vehicle here in a second. So this is exciting to me because we have never had this many cameras, and certainly not cameras of this quality on Mars, taking video, taking photo. So it's just very exciting to see that these missions are being so well documented by all the onboard cameras. Oh, wait, here we go. Let's move on. Okay. Okay. The big guy. Perseverance. This is the American mission. They landed just yesterday, the 18th. It was a flawless landing. Those space buffs in our audience may notice that Perseverance looks a little bit like Curiosity. And come to think of it, Insight looked a little bit like Phoenix, and Spirit looked awfully similar to Opportunity. So what's up with that? Well, it's economies of scale. It's a little bit cheaper to produce things in bulk. And so Perseverance has a number of spare parts from Curiosity that could have been used to help troubleshoot. If there was a problem with Curiosity on Mars, they could have built a replica here on Earth and tried to recreate the problem and test and find solutions. Anyway, some of those spare parts are now flying on Mars because we know that this general design works. With that said, it does have a different instrument layout. The core question of the Perseverance mission is basically, are there signs of life, microbial life? And by microbial, we mean like very small, right? Like really, really small, on Mars. We know there was water. We know that the atmosphere used to have more oxygen. We know that it used to be thicker. We know that the planet used to be warmer. So we know that it was fairly Earth-like billions of years ago. Could life have gotten hold there? Could life still be there now? All important questions. So they didn't give it a microscope. And we know that Curiosity was detecting methane as far back as 2014. This thing doesn't have any refined sensors to follow up on those methane detections in greater detail or anything like that. We also know that there are subterranean lakes, ice lakes, that sometimes will melt a little bit on the Martian equator in the summer and send these little cascading streams down the sides of craters. And they'll leave a salt deposit and then evaporate away after a number of days. Excuse me. Turns out Perseverance isn't checking on that either, isn't getting any water samples. It is still doing important work, but I would love to see NASA's budget increased a little bit so that they could go get a vehicle that could scale the sides of a crater and, for example, take a sample of that water. So what will Perseverance be doing? Well, they picked a very good landing site. Jezero Crater, it's about 28 miles wide. Can anybody tell me what this formation is here? Does this look familiar to anybody? Maybe any of our audience that's familiar with either Louisiana or Egypt? All right, I'll tell you. Feel free to chime in, guys. I hate talking to the walls.
We have
So
a pretty small group. We have a pretty small group, Seth. I think that we could. I'm just going to allow everybody to
oh, terrific.
if they wish. People have put their mutes on, but yeah, so people can answer you.
I like that plan. All right, well, we'll open it up to the floor here. Is anyone would anyone like to hazard a guess as to what you would call this feature here?
A delta?
Yes, that is a delta. As to what exactly formed it, we cannot say because we were not there, but this really, really looks like a river delta. And I mean, I'm no expert, but I don't know what else would produce patterns like that. Probably there was flowing water here in this river here. You got a little oxbow bend here. And then this river would flow out into Jezero Crater, which is about the size of Lake Tahoe here on Earth. And it deposited silt. And so Perseverance landed basically on or very, very nearly on this part of the, well, not exactly a riverbed, a delta. And this is geologically similar to Gale Crater, where Curiosity was making those methane detections. So there's a possibility of something similar happening here. And hopefully they'll detect biosignatures in other ways by looking at rocks and strange textures on the rocks. There are rock-like colonies of bacteria here on Earth called stomatolites, where the colony, as an old generation dies, a new colony, a new generation of these bacteria will kind of build up on these layers, until you have something that looks kind of like a mushroom, but actually is a colony of bacteria. If there was something similar to that, they should be able to find it on rocks in this area. So there's a number of instruments here on board the rover. We will not go over all of them. There are two that are particularly interesting with respect to detecting life on those rocks. There's the Sherlock and Pixel. So Sherlock can detect organic matter and materials, and Pixel can map the chemical composition of rocks and sediments. The instruments can work together to increase the probability of a biosignature detection. So anytime that you think you found something interesting, especially in science, you want to get the same result if you try in different multiple times, and you want to also maybe try different ways and get results that they make sense if you put them together, but they're maybe not the exact same result. And so that's why you would have an instrument like Sherlock and then an instrument like Pixel, staring at the same rock, making different detections, but then comparing them, and that would give you a stronger evidence for if you had detected life. The other really cool thing over here is MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. They love their word salad, NASA. MOXIE is going to take the carbon dioxide out of Mars's atmosphere, right? It's 95% of the atmosphere, not breathable for humans, but if you run a little electric current through that carbon dioxide, you produce oxygen and then carbon monoxide. So you get rid of the carbon monoxide, which is very deadly, very serious stuff, no good. And you're left with a ton of oxygen, which is breathable by humans and potentially useful for rocket fuel as well. So the electrochemical conversion requires a temperature of about almost 1500 degrees Fahrenheit, which is about 3 times hotter than most ovens here on Earth can produce. And so they actually had to plate it in gold to thermally insulate MOXIE from the other instruments on board the rover. It doesn't do a lot. It only makes about 6 to 10 grams of oxygen per hour, which would be about enough to keep a small dog alive. There are no dogs on the rover. They're not running that experiment, thank goodness. But it's a technology demonstrator. And if MOXIE is able to work well, then we can take that system and scale it up on the first human expedition. And it's important not just because that way humans will have air to breathe without having to bring all of that air with them from Earth, which is a lot of weight and a lot of cost, but also they may be able to make oxidizer, which is a very important part of the rocket fuel, and usually is the bulk of the weight of that rocket fuel. It's usually 2/3 or 3/4 oxidizer. And so they'd be able to save an incredible amount of weight by just pulling that oxygen out of Mars's atmosphere, and be able to breathe and essentially create rocket fuel. Okay, so the other really exciting thing to me, another technology demonstrator, is Ingenuity. So this is basically a drone. It is a counter-rotating twin rotor helicopter. It's a small one. Here's a little video of how it would operate. So it's actually deployed from the belly of the Curiosity rover. There's a complex kind of sequence of dropping it on the ground and then pulling away here. And there's a really curious bit of technology on board the drone, because Ingenuity is going to analyze its own flight instruments. It doesn't really have any scientific instruments, it's just got flight instruments. But it can use those to identify good routes through the terrain for the rover to then use. And so to give an aerial view like that could really improve the safety and efficiency and the speed with which a rover is able to navigate over the surface of Mars. Now, because the Martian atmosphere is so much less dense than Earth's, right? It's 0.5% as dense. So Ingenuity has to be incredibly light. It's about 4 pounds. The rotor blades have to be much, much wider, much broader, and they have to rotate much, much faster than a drone would have to here on Earth. Because Mars's gravity is so low, thankfully that at least is counting for the rotor, or sorry, for the helicopter. It doesn't need to create quite as much lift with the rotors because of the low gravity. But the thin air was more of a challenge than the low gravity was a help. Okay, you can see the cameras just photographing the surface, making sure that it's all flat, all good to go. And now it's going to land again. To save weight, Ingenuity really doesn't have that much in the way of batteries. So it can only fly for about 1.5 minutes before it needs to touch down and then recharge. And there we go. I think it's going to do that thing again. Let's see. Nope, there we go. Okay, so here is the Ingenuity drone or helicopter next to some people just for scale. And as you can see, it's really not that big. And you kind of heard this during that animation, but this drone is very, very loud. It's remarkable because the Martian air is so thin, it really doesn't conduct sound that well. So here we have a vacuum chamber, and so it's the air here is as thin as it would be on Mars, and it's also as cold as it would be on Mars in the chamber. And there are a couple of strings here. One of them provides a little bit of an upward pull to simulate Mars's gravity. And maybe you can hear just how annoying this is, the sound. I mean, it's a technological marvel. But this is just a very, very loud. Listen to that. So one of the reasons that a propeller is so loud here on Earth even is that parts of the airflow around the propeller blade are supersonic. And so a lot of the roar of a propeller doesn't actually come from the engine, but from these many tiny supersonic booms going all across the leading edge of the blade. And Ingenuity has a similar issue. So it's all par for the course. But man, you'd be able to hear that thing coming from like a mile away, huh?
Seth, I have a question about Ingenuity. Was it
Yeah.
on any other missions before?
No. This is the first time that we'll ever have a powered, controlled flight on another planet.
Wow.
And so this is a really big deal, because if you want to get technical, you could say, oh, well, there's been flight, because every Mars rover that's ever landed has had to kind of navigate its way down through the air. But that was ballistic, barely guided flight. This is something different altogether. So if it's successful, which I think it will be, but if this demonstration mission is successful, first of all, I think every rover in the future is going to have a helicopter. Second of all, we're going to see that helicopter given much more responsibility. There might be a high outcropping or a steep slope that a rover couldn't reach, that a helicopter could, to gather a sample or to study some rock or aspect of the soil. And even just seeing the role of the helicopter expanded for terrain navigation and identifying points of interest and points of danger, both. There's a lot of room to do more there. And so what Ingenuity is going to do is just demonstrate the basics, and that all of this is possible to do. And moving forward, I think we're going to see more distributed systems, that a spaceship isn't just going to be a spaceship, or an astronaut isn't just going to be a person in a suit, that there's going to be more and more of these systems kind of helping the mothership, so to speak, perform its many tasks. Yeah, this will be, long story short, this will be the first powered, controlled flight on another planet. Well, here's a story of unpowered, controlled flight. The entry, descent, and landing sequence here, this is also known as the 7 minutes of terror, because when Perseverance, in its heat shield here, enters the Martian atmosphere, it's going at almost 12,000 miles an hour. And it has to slow down to 0 miles an hour, and it's got 7 minutes to do it. The Martian air is just thick enough to cause an incredible amount of heat damage to the rover. However, it's not really thick enough to help it slow down in a meaningful way like Earth's atmosphere is for capsules that are returning through our atmosphere. So the shield is designed to brake as much as possible, but even with the parachute, it still is going too fast. So they use this the sky crane technology. So the sky crane actually has these rockets that fire, and it lowers the rover on a tether, and then the rover touches down, and the sky crane just kind of flies away. And there's already I didn't have time to put it in here, but there's already a photograph from the sky crane. They put a camera on it this time, looking down at Perseverance as it sets it down on the ground. Now, this maneuver has already been done before with Curiosity, so it is a technological marvel, to be sure, but it's not new. What is new is this terrain relative navigation. So this is a two-part system. You've got the lander vision system, which knows where the rover, or the lander, sorry, is over the Martian surface. And it has about 25 seconds to take a series of pictures of the surface and analyze those pictures for points of interest and points of danger. Then the lander vision system kicks its analysis over to the safe target selection system, which uses that position data and calculates where is the lander going to land right now, and then it's going to compare it to those hazards and those points of interest and decide whether or not to change course on the way down. Or again, this is all happening over 25 seconds or less. If the plotted location isn't suitable, then safe target selection can change the rover's where it's headed, basically, by changing their attitude and drifting around in the atmosphere, a little bit like what a skydiver can do. And it'll be able to move the landing point by about 2,000 feet in any direction to avoid any danger. And I'm happy to say that this system worked perfectly. Now, what I haven't gotten a report of is whether or not it was necessary. I don't know if Perseverance avoided any obstacles on the way down to demonstrate that the system worked, or whether it just so happened to be heading towards a perfect site, and so safe target selection didn't have to take over and adjust course. But obviously the system worked, because that was a flawless touchdown. The extent to which it worked, I'm sure, will be reported on. And that's another, to me, the most exciting parts of the mission really are technology demonstration. We've got Moxie creating oxygen out of an unbreathable atmosphere. We've got Ingenuity, first powered controlled flight on another planet, and probably the start of many rover drone pairings. And we've got this terrain relative navigation system, and it's going to make future landings more convenient and more reliable, and probably something very similar is going to be used to land humans on Mars to reduce the risk even further by having essentially a low-level AI pick the safest landing spot on the way down. So would anybody like to guess? It's just Nancy in it. Well, Nancy, can you guess how Maine is actually involved with this rover?
Heat shield?
Yeah, yeah, exactly. This is an internal shot of Fiber Materials Incorporated in Biddeford. These guys fabricated, we call it a heat shield. They call it a thermal protection system. And they used a material called pica, and they did the Curiosity heat shield, so now they're doing the Perseverance one. This is now the largest heat shield that's ever been built, ever. And the goal is to protect the rover from those temperatures during landing, which can reach like 3,500 degrees, incredibly hot, and they need to keep the rover at very nearly room temperature. So no small feat. And so that amazing little piece of technology came out of FMI right here in Maine. Now they're also responsible for the aeroshell on the Space Launch System that will protect the Orion crew capsule. So these guys are actually really, really heavily involved in space exploration, and I'm proud to be in the same state as these guys. All right, that concludes the presentation. But of course, I'm happy to take any questions. Oh, got one. Is Ingenuity on board the Perseverance? Yes, it is. It is stored right around the middle of the bottom of Perseverance. So when the rover finds a nice, smooth, flat patch of Martian surface there, it will just drop the helicopter down. I mean, there's a process to it. The helicopter has to unfold and it has to deploy some landing gear. But once that's all done, then Perseverance just drops Ingenuity a couple inches down to the surface and then just rolls away. And then from there, Ingenuity flies on its own.
Seth, how long will the rover be there?
Well, that really depends. It's powered by a nuclear generator, and as a result, I would guess that it could probably run 20, 30 years. Now, the primary mission doesn't go nearly that long because a number of things could go wrong in that time. They have to account for the wear of that Martian dust on all of the other rover components.
So when NASA sends a rover, does it expect it to see it again? It doesn't come back.
It doesn't come back. And the Jet Propulsion Laboratory has been really amazing about over-engineering their rovers. So Spirit and Opportunity both were supposed to last about 3 months, and they did, I think Opportunity did about 12 years. And so I wouldn't be surprised if we were pleasantly surprised also by the performance of Curiosity and Perseverance. There was a plan for a Mars sample return mission, and we see about half of it actually in this lander. Perseverance is going to take samples, and it's going to store them in a little carousel. I think it can hold like 45 samples of Martian dirt or drilled rock in essentially a sealed test tube. And so it's going to fill up all of those sample containers. And then sometime down the road, at the command from the engineers here on Earth, it will just drop the carousel in a manner similar to the Ingenuity drone, and then it'll just kind of roll away. The plan is down the road, another mission, maybe it'll be crewed, maybe it'll be robotic, is going to come pick up those samples and then bring it back to Earth.
Wow.
Yeah. This is probably, well, how do you define complexity really? Originally, Mars Samples Return was going to land on Mars, take a series of samples, and then launch a small rocket and return the sample to Earth directly. But now it's kind of become this two-phase mission. So we'll see. We'll see how it goes. At the very least, the sample collection will be another technology demonstrator for another mission that is able to integrate the collection with the sample return and launching that small rocket back. One of the nice things about getting back to Earth from Mars is that because the gravity is so much weaker on Mars and because the atmosphere is so much thinner, you don't need nearly as much rocket fuel to get into orbit. And so especially with a small little, kind of a carousel of samples, about this big, you could get away with a pretty small rocket to do that. How long did Perseverance take to build? I'm so sorry. I really don't know. That's a good question. I can look it up. Want to go on a journey with me here? Well, that doesn't tell us anything, does it? Well, I'm going to guess 1.5 years. Let's see how we do. Prime mission operations, 2 years. Okay. I can tell you it took about 6 or 7 months to get to Mars. 11 years. Okay, well that includes planning phases though. That definitely does not include construction. And that's Wikipedia. I do not encourage, well, trust but verify, right? Let's see. Yeah, I don't know how, I don't know that we're going to get a number just off the front page of Google. Sorry, I tried. I can answer that down the road, maybe if there's a way to do follow-ups.
Sure, there is a way to do follow-ups. Well,
okay.
Once this recording is ready, we'll send it to the participants just in case they want to share it with anybody else. Okay. And we can send answers to questions too.
Excellent.
Same time.
Well, I'll try and have something by tomorrow. We'll see. Yeah. Anybody else?
I don't think we have any more questions
Oh man. All right.
at this point. It's pretty amazing. I was enjoying the news coverage
Nice.
yesterday when the rover stuck the landing.
Oh my God.
And I thought that was such a huge crowd cheering. It made me
Yes.
curious about how many people are on the team.
Oh, that's another really good question that I just don't know. Yeah. And then of course there are many teams involved in the process of launching, you know, because there's a whole team associated with just the launch vehicle, and I think that as part of the Perseverance team was in charge of the transfer vehicle. But yeah, no, it's I don't know. I'll see what I can get on that number as well. But yeah, it's always a little harrowing to watch a Mars landing, because so far about 40% of them have worked out, and so our reliability has improved dramatically in the past couple of years, to the point that one of the landers, I believe, did not even have a communications blackout. So our reliability on these landings has really gone up, basically since the Pathfinder back in the 90s. But you still never know. Something could still go wrong.
It's amazing. I didn't realize that previous missions only had a 40% accuracy.
Yeah, some of them were really painful. I mean, some of them, you know, for those orbiter missions, you have to slow down to get into orbit, right? And so one of them, they mistimed the firing of the engines because there was a confusion. There was a collaboration with the European Space Agency, and I don't even know how this happened, because most scientists and engineers, they mostly just use the metric system in their day-to-day anyway. But somehow one of the flight systems confused imperial units there with metric, and so it didn't go right, and so the probe just, you know, kind of went on past Mars.
Oh, wow.
Yeah, so sometimes it's just the silliest, simplest thing that, like, who would have even thought to have checked that, right? But
Right.
yeah, sometimes that's what gets you, right? And here on Earth, you can be like, ah, ha, 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 silly me, and then just use the other side of the ruler or whatever it is, you know. But when your computer is autonomously decision making, you know, 140 million miles away, you just don't have that kind of, you know, forgiving margin of error. Yeah.
Seth, can you hear me okay?
Yeah.
Hi, I just wanted to share there was a question about how long it took to build. My dad was an aerospace engineer, and he participated in the Galileo probe to Jupiter, and his
No
role
kidding.
was as a subcontractor, and he worked on the reentry system, particularly the shield and the parachute reentry, meaning into the planet's atmosphere. He started his work as a subcontractor in 1977, and the probe didn't go, well, it started to release in 1995. So that gives a sense of how long these things take from a twinkle in somebody's eye and a mission approved to the research and development process, which I think is fascinating. He retired and never had a chance to see the probe actually succeed, because that's how long it took. And he lived into his late 90s. So
Wow.
it really takes dedication from an awful lot of people. So when you see those folks jumping in the control space, it's, you know, talk about on the shoulder of giants. They have a huge debt for an awful lot of scientists and ingenious people in the background. So Mike, I kudos to all of you, because I know you're working on some really innovative stuff now too, Seth. So it's, my dad would
Thank
love
you.
it. He was a University of Maine grad, and went into aerospace with his mechanical engineering degree from Orono.
Wow. Wow, that's amazing, because we need more aerospace engineers, and we don't really have a aerospace engineering program per se. So that was a problem even back then.
Yeah, he started with heat transfer as his specialty,
Okay.
and started working on, well, in those days it was World War II, and how to heat the cabin of the airplanes as the military aircraft went over the hump in Burma to keep the pilots warm
Yeah.
enough.
Wow.
And
Wow.
then he worked on altitude chambers, and then went into heat transfer after that, using his work on nose cones and ballistic missiles and all kinds of other stuff that then finally took him into the space world.
Wow. Wow, that's amazing. God, I guess I owe him a debt of gratitude, because the whole solar system ambassadors program got started for the Galileo mission.
Wow,
Yeah,
that's very cool.
small world.
Yeah, that's wonderful. Well, I still have his notes. He used to go out and speak to Rotary clubs.
Can I see those notes, Nancy?
Sure, I'll share.
Thank you. That's amazing. Wow. Thank you.
Well, I have another fun story. You were talking about the
Yeah,
very
please.
sophisticated measurements, and just the importance of measuring it with the right measurement system. My dad was a subcontractor working with GE, which is the group responsible for the reentry piece.
Mhm.
He worked for Hughes Aircraft at the time, but he was,
Wow,
this
wow.
is going to be a little esoteric, but he was also a barbershop quartet singer. So he had a pitch pipe. And
Okay.
he told a funny story about them having to test the tension on the parachute cord while they were
Harmonic
testing
resonance, right?
bucks, and he was able to use his pitch pipe to determine whether they had the right resonance on the parachute cords. Now, of course,
Wow.
that was only a model. They wouldn't use that in the final version, but it helped him in terms of testing out parachute cord tension. So I thought that was kind of a fun story.
Wow.
Innovation.
Yes. Absolutely. That's engineers for you, though. They're always using stuff for something very much other than its intended purpose, right?
Biofuels.
Exactly. Exactly. All right. Well, yeah, I guess if that's it for this evening, maybe I'll come back next evening. I don't know.
Oh, that'd be fun.
How do you think, Lucy?
Definitely.
All right.
Yeah.
Yeah.
Well, thank you very, very much.
Absolutely. My pleasure. All right. Well, have a good evening, all.
Thank you. You too, Seth.
Goodbye,
Thanks.
everybody. Seth, we'll
Bye.
see you tomorrow.
See you then.